Preface. A crash course in statistics delves into key statistical methods, namely chi-square, t-test, ANOVA, and descriptive statistics. It equally gives an overview of statistical methods, as well as various discussions of the statistical tests relating to various databases culled from various sources, like the survey of student spending on textbooks, etc. Also, detailed demonstration of various data analysis in SPSS was considered via statistical test. Descriptive statistics, being an outstanding aspect of this broad field, was considered in detail, as well as the field of nonparametric statistics. Furthermore, this text will look into the one-way and the two-way statistics. Parametric and nonparametric statistics is a very important aspect of the subject matter, thereby necessitating their mention in this text. Mention will be made of their theories and practical aspect towards enlightening the reader about how each of them is applied in real-life situations. Also, the reader will get enlightened on how each of these statistical methods differs. Aside from the basic concepts of probability that will be discussed in this text, mention will equally be made of conditional probability, probability description, and discrete random variables. Besides, the relationship between probability distribution and continuous random variables will be mentioned. Additionally, the text will discuss the central limit theorem as well as the sampling distribution of the sample mean. As much as possible, this write-up will only focus on the basics and foundational aspects of the field of statistics, since the purpose is focused mainly on building a foundation of the subject matter. Introduction. In the short run, it is somewhat difficult to predict chance behaviors. However, probability or chance behavior shows a predictable pattern when considered in the long run. Also, the random phenomenon relating to the probability of a particular outcome is proportional to the number of times such an outcome occurs in a series of repetitions. Sample space refers to a set of all the possible outcomes that can exist in a random phenomenon, while the term event refers to a particular set of outcomes of desired interest. The probability of a particular event refers to the frequency of a set of outcomes compared to a given infinite number of trials. If two events occur right at the same time, such two events are said to be mutually exclusive. If the occurrence of two events does not depend on each other, however, the two events are said to be independent events. Interpreting a set of data on its own is somewhat uneasy since much hidden information is present in such a set of data. Statistical methods have proved useful for understanding and interpreting the data, towards getting them summarized in a more meaningful way. Summary of statistics and graphs have proved to be very useful for these purposes. With the aid of graphs and other statistical tools, it is easy to detect the major features of a data and also to find out which data is recorded correctly and which is not. Furthermore, statistical methods can be used to detect outliers, which are very extreme observations that are not consistent with other available data. Many of the formal statistical techniques available today can be distorted by the presence of outliers. This brings to the fore the importance of preliminary accommodation, correction, and detection of such aberrant observations, after which further analysis can occur. Lesson 1. Methods of data representation. Frequency table. The shape of any distribution from random variables requires in-depth investigation, and this is best done using frequency tables as well as diagrams. The frequency table categorizes data observation entirely in an easily interpretable manner. The categories adopted for discrete quantitative and qualitative data is represented by the observed values. Combined categories are formulated from consecutive observations if a large number of various observations are involved. Category choice for continuous data is somewhat more arbitrary, leading to the adoption of 8 to 12 non-overlapping consecutive intervals having equal width. If small shape sizes are being dealt with, on the other hand, it is better to adopt fewer numbers of intervals than the above. Histograms. The histogram is one of the pictorial representation of the data outlined in the frequency table. It is, however, the most popular pictorial representation for many of the continuous data sets in statistics. In the histogram, the intervals are outlined to scale on the x-axis of the graph, and various representative rectangles are drawn to ensure the frequencies are proportional to their areas. The y-axis, therefore, represents the relative frequency per unit class interval. There is always proportionality between the frequencies and the height of the rectangles, provided the statistician uses class intervals having equality to the width of the rectangle. The area under the histogram is always unitary whenever the y-axis is labelled using the relative frequencies. Bar charts and frequency polygons. The data are best displayed pictorially in the form of bar chart when the frequencies point to individual values and the data are discrete. They can also be represented in frequency polygons in place of a bar chart. In frequency polygon, only the top parts of the bars are marked, and each of the marks is joined with a straight line. Gaps are left between neighbouring rectangles or bars when bar charts are being drawn, which makes them easy to differentiate from histograms. Two or more data sets are best compared to one another using frequency polygons. The pie chart is yet another method of data presentation, and it is representative of qualitative data. It involves the use of a circle divided from its centre into sectors. The angles and areas of each of the sectors are representative of the frequencies in each of these categories. In general, the pie chart is not applied in quantitative data. Instead, statisticians prefer frequency polygon or bar chart. It is very important to provide descriptive title along with any graph, as well as a properly labelled axis for easy understanding and interpretation. Stem and leaf plots. Discrete and continuous data can be best represented using stem and leaf plots, especially if the sample size is not up to 200. There is a similarity between the stem and leaf plot, histogram and bar chart. Interval of 5 to 12 is also desired in this method of data presentation, just like what obtains in a histogram and bar chart. The width of the interval should, however, be 0.2, 0.5 or 1.0 times the power of 10 for stem and leaf plots. With stem and leaf plot, it is very easy to depict the general shape of the data you want to represent. The various methods of data presentation described above can provide an empirical understanding of the various cogent features of any particular data distribution. They can show if the data is symmetry or otherwise. They can also show if there is any outlying or unusual observation. The various methods can equally show if the data in question is multinodal or not. This will tell if there are multiple peaks or gaps in the data presentation. If there are two peaks, it can be an indication that the data represent two different groups. The distribution of different groups of data can equally be compared by simply putting plots with the same scales side by side. Lesson 2. Summary measures. Measures of location. The statistician needs to obtain the quantitative summaries of specific aspects of data aside from the various graphical techniques that had been discussed in the previous chapter. Many of the simple summary measurements can be easily categorized in two forms, which are the quantities that summarize data variability, also called the measures of locations, and quantities that are typical of the special data, also called measures of spread. Sample mean. It is recognized as the most widely used and the most important measure of location. It is the only mostly used when referring to the average value of a set of data. When dealing with continuous data, it is better to calculate the sample means from the original data, provided the latter is known. If the original data is not known, however, then one can estimate the sample means by reaching an assumption that all data sets occurred at the midpoint of that internal, provided the data is tabulated in a frequency table. Sample median. This talks about the middle observation when a particular set of data is arranged in increasing order. The sample mean of the middle two numbers will represent the median if there is no middle number, but a set of even numbers. Instead of using the sample means, many statisticians prefer to use the sample median. This is the case especially when the set of data under consideration contain outliers or are asymmetric. The mathematical properties of the sample means are easier to determine than those of the sample median. However, This is one important factor that makes the sample mean somewhat preferred by some statisticians for various normal statistical analysis. When working by hand, it is preferable to calculate the median using the stem and leaf plot. The computer is, however, used if a bulk of data is being handled. Sample mode. The mode of a set of data represents the particular value or number that occurs most often in that set of data, that is, the number with the highest frequency. As a result, the mode is best used or calculated with discrete data. The most important measure of location is the sample mean, which is due to its highly attractive mathematical properties. Whenever a symmetric value of the data distribution is obtained, the various values will be in proximity to one another. Some considerable differences may, however, occur if the distribution is skewed, leading to the use of all the measures for a better understanding of the data. Sample media has been discovered to be more robust as a location estimator, and it is also less sensitive to unusual values of data and asymmetries compared to the sample mean. When skewed data is obtained, associated problems can be overcome by transforming the data, which will produce a more symmetric distribution. The data is called a negatively skewed or left-skewed data if it features a longer tail on the left. In the same vein, the data is said to be positively skewed or right-skewed if it possesses a longer tail on the right. Many people expect the term described above to mean something different, since the major part of data distribution is automatically shifted to the opposite direction. Logs of data of square roots may be useful in solving the problem if the data is right-skewed. The data can, however, be exponentiated or squared if it is negatively skewed. Measure of spread. It is not enough to know the typical value of the data alone. There is also need to know how spread out or concentrated the data is. This means knowledge of the variability of the data is very important. We can numerically quantify this idea using a measure of spread. Range. The range of a set of data represents the difference between the smallest and the largest observation or number. The range can be useful in comparing sample variability if the samples are not robust but have the same size. It cannot be used in comparing the variability of various size samples, and it is not a fixed population characteristic. Mean absolute deviation, MAD. It represents the average absolute deviation from the sample mean, and it is very easy to understand, making it useful for even non-statisticians to utilize. Variance and standard deviation, which is the square root of the former, are, however, preferred ahead of MAD for very strong practical and theoretical reasons. Sample variance and standard deviation. It represents the average squared distance from the mean value of a set of data. This value simply represents the square root of the sample variance. It is provided in the units of the original data and, therefore, preferred as a summary measure. Statisticians, however, find it easier to work with variance since it is better from a theoretical point of view, making the two measures to be complementary. The standard deviation can be calculated using various methods by many calculators. When standard deviation, mean, or any other summary statistic is being calculated, it is very important to have ideas of the possible value to spot any arithmetic mistake or slip when the set of data is being entered into a computer or calculator. It is also important for the sample mean to be near typical values in a set of data. Quartiles and the interquartile range. The lower quartile has a quarter of the data less than it, unlike the median that has half of the data less than it. The upper quartile, on the other hand, has a quarter of the data above it. If the value obtained from these calculations is not an integer, it is necessary to interpolate between adjacent observations linearly. Coefficient of variation. The coefficient of variation represents a measure of spread that can be of interest. It is also referred to as the ratio of the standard deviation of the mean, and it therefore has no unit. Change in the scale, but not the location of the data, does not lead to change in the coefficient of variation. This means the coefficient of variation will turn out to be the same for a given set of length measurements, either measured in inches or centimeters. For temperature measurements in either Fahrenheit or Celsius, there will be the difference in coefficient of variation. Box and whisker plots. It has become a very useful graphical description of the features of a given set of observations. Many variations occur on the box plot, and the simplest form of the box and whisker plots can be made by drawing a box stretching from the upper quartile to the lower quartile, and then dividing the box into two at the median part. A line is drawn from each of the ends of the box to the minimum and the maximum observations, and these lines can sometimes be referred to as whiskers. This is where the graphical description got its name. They are very useful in making comparison among groups of observations. It involves constructing a box for each group, and the boxes are later displayed using a common scale. There is a need for a minimum of 10 observations if the box is to be meaningful. Lesson 3. Introduction to Probability. Sample, sets, events, and spaces. Uncertainty is modelled using the term probability. In this chapter, the probability theory fundamentals will be considered. They have proved to be an integral part of statistics and will, therefore, reflect in the remaining chapters of this text. They are useful for modelling experimental outcomes, as some of those discussed earlier. Sample spaces. Probability theory is used as a model for specific situations when the outcome occurs randomly. Such situations are referred to as experiments. Also, a set of all the possible outcomes of such experiment is called sample space that corresponds to any given experiment. The sample's space is selected in such a way that only an outcome will ever occur. Its size is uncomfortably infinite, countable infinite, or finite. Events. An event refers to the subset of any sample space, which is the collection of all possible outcomes, and they can be categorized into 4 different types, which are: first, the sample space itself; second, a compound event, which is a subset comprising more than a single element of the sample space; third, an atomic event, which is a subset comprising single element of the sample space; fourth, the null event, which comprises the empty subset of the sample space. Set theory. Sets are very common phenomena, same for others like the intersection of two sets, union of two sets and complements of sets. The basic rules of the set theory are listed below. First, commutative laws. Second, associative laws. Third, distributive laws. Fourth, De Morgan's laws. Fifth, disjoint union. Sets can be easily manipulated by using what is called the Venn diagram. Be that as it may, these set of laws highlighted above are the main elements on which formal proof of set theoretic relationships should depend. Interpretation of probability. A term called axioms successfully captures the essence of probability in a mathematical form. Probability theory needs to possess an interpretation that connects to reality for it to appear as anything better than just abstract mathematics. No need to search for interpretation, however, if the individual is only interested in studying probability as an ordinary mathematical theory. If the interest is in using probability theory as one of the foundations or inference, the theory of statistical inference, then there is need to worry about probability interpretation. Such interpretation brings about some connection between reality and mathematical theory. Some disagreements exist regarding the interpretation of probability, despite the unanimous agreement about consequences of axioms and mathematics of probability. Below are the 3 major interpretations available. Classical interpretation. This has its basis on the assumption of underlying events that are likely. This means there is always sample space for any event that is under consideration, and such an event can be considered anywhere all atomic events are likely. The probability axioms may be derived from considerations of set theory provided the sample space is given. When there are obvious facts on how space sample can be partitioned into similar events, then the interpretation is applicable. Computation of the interpretation is not likely, which is the major problem associated with this type of interpretation. The above reason is why the classical interpretation is not considered as a good representative of practical problems. Be that as it may, it still makes available very good starting point for probability theory's mathematical treatment. It is equally the adopted interpretation by several theoreticians and mathematicians. Frequentist interpretation. It is also referred to the relative frequency interpretational, and it is the adopted probability interpretation by many statisticians. In comparison to the classical interpretation, there is a stronger connection between this form of interpretation and real-world situations. It equally fits perfectly well with the traditional statistical methodology. Probability, in this case, has meaning only in events derived from experiments which can be arbitrarily repeated, in principle, several times under identical conditions. Subjective interpretation. The subjective interpretation has some controversies that are associated with it. Be that as it may, it is still not subject to the problems associated with the other forms of interpretation. According to the subjective interpretation, probability association to events is a personal or subjective process which has a relationship with the degree of belief that an event will occur. The controversial aspect of this form of interpretation is in the fact that different individuals will attach different probabilities to similar events. Lesson 4. Descriptive statistics. This is the form of statistics that summarizes or describes the features of series of information quantitatively. There is a difference between inferential statistics, also called inductive statistics, and descriptive statistics. The latter is focused on summarizing a given sample of data, while the former is focused on using the data for learning about the population of data sample represents. Inferential statistics are developed by probability theory discussed earlier, while descriptive statistics is not. Descriptive statistics are almost always present whenever the main conclusion is drawn in data analysis using inferential statistics. In a given paper or document reporting about human subjects, a table is usually included, which will give overall clinical characteristics, demographic characteristics, sample sizes, and so on. A measure of variability and measure of central tendency are some of the commonly used measures in describing a set of data. Some of the commonly used measures of central tendency are the mode, median, and mean. On the other hand, measures of variability can be done using skewness, kurtosis, the maximum value of variables, minimum value of variables, standard deviation, and variance. Use of statistical analysis. Descriptive statistics gives very simple summary regarding the sample being considered and also about the various observations that are deduced. The summaries may be visual or quantitative. The visual can come in the form of easy-to-understand graphs, while the quantitative summary can come in the form of summary statistics. The summaries in discuss may enough for carrying out the potential investigation, or may form the basis of an initial description of the data, being an integral part of a far more extensive statistical analysis. The performance of a basketball team, for example, can be summarized using shooting percentage in basketball, which is a form of descriptive statistics. This is expressed as the number of shots that are made divided by the number take. This means that any player that shoots 33% will make one shot in 3, approximately. The percentage is useful for describing or summarizing multiple discrete events. A grade point average is defined as a single number describing a student's general performance across experiences in a range of courses. The use of both summary and descriptive statistics has quite a history behind it. The statistics topic first came up in the form of economic and population data tabulation. In recent times, a set of summarization techniques have been formulated and called exploratory data analysis. One of such techniques is the box plot. Different forms of data can be perfectly summarized using descriptive statistics in the business world. For example, brokers and investors can make use of the historic account of return behaviors by carrying out analytical and empirical analysis on their various investments towards making better investing decisions in the future. Univariate analysis. This swoons around the description of a single variant like central tendency, namely mode, median and mean, and dispersion, which includes the measure of spread such as standard deviation and the variance, quartiles and the range of data. The distributional shape may equally be described using indices like kurtosis and skewness. Stem and leaf display, histograms, and several other tabular and graphical formats can equally be used to depict the characteristics of a variable distribution. Bivariate and multivariate analysis. Bivariate and multivariate refer to samples consisting of more than a variable. When such samples occur, descriptive statistics can then be applied in describing the relationship between various pairs of variables in this situation. Descriptive statistics can be classified into, first, description of conditional distributions, second, quantitative measures of dependence, third, graphical representation via scatter plots, fourth, cross-tabulation and contingency tables. Bivariate and univariate analysis are differentiated especially because bivariate is a simple descriptive analysis and also describes the relationship between two individual variables. Examples of a quantitative measure of dependence include Spearman throw and Pearson's R. The former is applicable when one or both variables are continuous, while the latter is applicable only when the two variables are continuous. The other example is covariance, which is a reflection of the scale on which variables are measured. The relationship between the two variables is also reflected via the slope in regression analysis. The slope may be standardized or unstandardized. The former is an indication of a change in standardized units, called z-score, while the latter is an indication of a unit change in the variable of the criterion for single unit change in the predictor. There is need to take logarithm when analyzing highly skewed data. This will make the graph to have more similarity to the normal distribution and also to look more symmetrical, thereby making the graph far easier to interpret. Lesson 5. Parametric and nonparametric statistics. Nonparametric statistics. Nonparametric statistics are a set of statistics that do not have their basis on parameterized families of distribution probability. These include both inferential and descriptive statistics, and the typical parameters used are the variance, mean, and so on. While parametric statistics assume the distribution probability of any given variable under assessment, the same cannot be said about nonparametric statistics. Parametric models are different from non-parametric models in that parametric models have fixed number of parameters and the latter increases its number of parameters using the number of training data. It is also important to note that non-parametric models do not contain parameters, which is counterintuitive. In the case of non-parametric statistics, training data is used in determining parameters, unlike what obtains in non-parametric models. The term non-parametric statistics can be accorded with two meanings in statistics. First, the first meaning has to do with various techniques that have no reliance on data related to any given distribution, and these include distribution-free methods and non-parametric statistics. In distribution-free methods, there is no reliance on assumptions stating that the data under analysis are derived from any given probability distribution. As a result of this, distribution-free method is seen as an opposite of parametric statistics. Distribution-free methods include statistical tests, inference, statistical models, and descriptive statistics. Non-parametric statistics, on the other hand, is defined as a function on any sample that does not depend on a parameter, and its interpretation has no reliance on population that fits any form of parameterized distributions. Order statistics is one of the examples of this non-parametric statistics and has its basis on the ranks of observations. It equally plays a very important role in several non-parametric approaches. Second, the second meaning has to do with various techniques that do not see the structure of any model as being fixed. Over time, the model will increase in size, enabling it to accommodate any complexity that may exist in the data. In this set of techniques, each of the variables are assumed to be part of the parametric distribution. Also, assumption is made about the various types of connections that exist among the variables. Good examples of these techniques are nonparametric regression and nonparametric hierarchical Bayesian models. The former example talks about modeling in which variables' relationship structure is handled nonparametrically. However, there may be some parametric assumptions regarding the distribution of model residuals. Models that are based on the Dirichlet process are examples of non-parametric hierarchical Bayesian models, and it permits the number of latent variables to increase as an important fit to data. Parametric distribution is followed by the rate of latent variables growth and individual variables. Application and purpose of nonparametric statistics. Any population that is presented in the form of ranked order can be studied using nonparametric statistics. Good example of this is movie review. When data do not have clear numerical interpretation but only possess ranking, then nonparametric statistics can be necessary. Example of this is in assessing preferences. Nonparametric statistics also results in ordinal data in terms of levels of measurement. Fewer assumptions are made in nonparametric methods. Therefore, they have wider applications than parametric methods. If very little information is available about a particular application, then nonparametric methods can be applied in such situation. Nonparametric methods are highly robust due to the fact that they do not rely much on assumptions. Simplicity is one of the other justifications for the application of nonparametric statistics. It can be easier to use nonparametric methods even in certain situations in which the use of parametric method may be justified. Nonparametric methods leave little space for misunderstanding and improper use due to its robustness and simplicity. Nonparametric methods may be highly robust and have wider applicability, but it comes at a cost. Nonparametric tests have far less power in situations where parametric tests are appropriate. For example, one can draw a conclusion from a larger sample size having equal degree of confidence. Nonparametric models. Nonparametric models have a structure that is determined from data instead of being specific in advance. It should be noted that being nonparametric does not mean the models do not have any parameter. It only means that the nature and number of parameters are not fixed in advance, but flexible. Examples of nonparametric models are listed below. First, a histogram, which is used in nonparametric estimation of a probability distribution. Second, kernel density estimation, which provides a better estimate of the data density compared to histograms. Third, semiparametric regression and nonparametric regression methods, which are developed based on wavelets, splines, and kernels. Fourth, data envelopment analysis, which makes available highly efficient coefficients that have similarity to the ones gotten through multivariate analysis in the absence of distributional assumptions. Fifth, KNNs, which can be used in classifying several unseen instances that are based on the K-points in the nearest training sets. Sixth, support vector machine, which is used as a nonparametric classifier having large margin. Seventh, artificial neural networks, which is an extension of nonparametric models. Methods. Distribution-free or nonparametric interferial statistical methods are defined as mathematical procedures used in statistical hypothesis testing and do not make any assumption regarding distribution probability of variables under assessment, unlike what obtains in parametric statistics. The tests used most frequently are highlighted below. First, Wilcoxon-signed rank tests, which can be used in testing whether matched pair of samples are derived from populations having different mean ranks. Second, analysis of similarities. Third, Wold-Wolfowitz-Runge test, which tests the elements of a sequence to find out if they are mutually random or independent. Fourth, Anderson-Darling test, which can be used in testing whether a given sample got its origin from a particular set of distribution. Fifth, Turkey-Duckworth test, which can be used in testing the equality of two different distributions using ranks. Sixth, statistical bootstrap methods, which is used in estimating the sampling and accuracy distribution of statistics. Seventh, squared rank test, which can be used in testing the equality of variance in several samples. Eighth, Cochrane skew, which is used for testing K-treatments possess similar effects in randomized block designs. Ninth, Spearman's rank correlation coefficient, which is used in measuring statistical dependence that occurs between two given variables using monotonic functions. 10th, Cohen's kappa, which is perfect for measuring inter-rater agreement for various categorical items. 11th, sign test, which is perfect for testing if matched pair samples can be drawn from distributions having equal medians. 12th, Friedman two-way analysis of variance by ranks works just like Cochrane's Q for testing if K-treatments possess identical effects in randomized block designs. 13th, Siegel-Turkey test, which is perfect for testing the difference in scale existing between two different groups. 14th, Kaplan-Meier, which is used in estimating the survival function from lifetime modeling data censoring. 15th, rank products, which helps in detecting differentially expressed genes present in replicated microarray experiments. 16th, Kendall's tau, which is perfect for measuring statistical dependence between two different variables. 17th, Pitman's permutation test, which is useful in generating exact p-values in detailed examination of every possible label rearrangements. 18th, Kendall's W, which is simply a measure between 0 and 1 of inter-rater agreement. 19th, median test, which is useful in testing if two different samples get their origins from distributions having equal medians. 20th, Kolmogorov-Smirnov test, which tests if a given sample is drawn from a given distribution or if two different samples are obtained from similar distribution. Parametric statistics. This branch of statistics relies on assumption, unlike what obtains in the non-parametric statistics. It is based on the fact that a sample data are derived from a given population related to distribution probability having its basis on a fixed set of parameters. Many of the popular elementary statistical methods are parametric. As had been shown in the previous chapter, a non-parametric model has parameter set that can increase or decrease since it is not fixed. The variability occurs any time relevant information is obtained. As hinted earlier, the parametric model assumes more than the non-parametric model, especially since the former relies on a fixed parameter set. Parametric methods produce more precise and accurate estimates than the non-parametric methods when the assumptions are correct. This means the parametric methods possess higher statistical power. They can, however, fail because more assumption is made, leading to the increased chance of incorrectness. Their increased chance of failure counts the parametric methods out among robust statistical methods. Be that as it may, parametric formulae are still faster to compute and easier to write down than the latter. Their lack of robustness is compensated by this simplicity, especially if one properly examines diagnostic statistics. The normal group of distributions is parameterized by standard deviation and mean, as well as having a similar shape. This means that one can deduce the probability of any future observation provided one knows the normalcy of the distribution, its standard deviation and mean. Lesson 6. One-way ANOVA. ANOVA stands for Analysis of Variance, and one-way ANOVA refers to a unique technique used in comparing the means of several samples with the aid of the F distribution. The technique is only useful for numerical response data and numerical categorical input data, both of which are one variable or one way. The null hypothesis has it that samples found in all groups are derived from populations having similar mean value. The ANOVA is used in testing this hypothesis. There is need to make two estimates of population variance. The estimates have their basis on different assumptions. The F statistic represents the ratio obtained from variance calculation among the means compared to the means in the samples. The variance occurring between the two groups' means are expected to be lower than the variance of the sample, provided the group means are derived from populations having similar values in line with the central limit theorem. If the ratio is of higher value, it means that the samples were obtained from a given population having different mean values. Typically, one-way ANOVA is useful in trusting the differences existing among a minimum of 3 groups. This is because the two-group case can be adequately covered by using a t-test. The f-test and the t-test are equivalents whenever only two means need to be compared. The core ANOVA analysis is made up of several calculations, the data of which is collected in tabular form. First, each of the treatment groups is summarized using the number of the variants, a mean, 2 sums and experimental units. A total of the sums and number of units are derived by the combination of summaries of the treatment group. Then, the grand variance and grand means, and calculating using the grand sums. The model is then deduced from the grand mean and treatment means. Second, the SSs and DFs can be computed using the summaries. The F is determined by a ratio after the MSs are computed. Third, the p-value is determined from F using a computer which can produce considerably different results. There is validity in the model if the result is significant. If the experimental units are all homogeneous, as is the case in a more complex experiment, the analysis can also benefit from row statistics. Two-way ANOVA is a statistical test used in determining the effect of 2 different predictor variables, nominal in nature, on a continuous outcome variable. This phenomenon is useful in analyzing the possible effect of independent variables on what he expected the outcome would be, as well as their relationship to the particular outcome. There is no statistical influence on a data set by random factors. However, systematic factors have such statistical significance. It is important to carry out the ANOVA test for way identification of the factors influencing any given outcome. The tester can carry out an additional test on any systematic factor contributing to variability of the data set. The result obtained from the ANOVA test can therefore be used in F-test to determine the significance of the regression overall formulae. Conclusion. This write-up has delved deeply into various statistical methods, thereby opening the eyes of the reader to the several important considerations regarding the field of statistics. Mention was made of the idea of probability and the various forms of data presentation methods in the field of statistics. Also, the applications of each of the data presentation methods were discussed, thereby enlightening the reader about each of these methods of data presentation and their importance as well as real-life application. The place of importance occupied by parametric and nonparametric methods in the field of statistics were also discussed, which led to an exposition of the differences and similarities between the two phenomena. Mention was made of specific situations warranting the application of either of them and their various practical utility. One-way ANOVA and two-way ANOVA were also discussed, with special emphasis on how each of them applies to real-life situation, not also forgetting how they compare to each other. The text focuses on the theoretical and the practical aspects of statistics, keeping in mind that one cannot exist without the other and that the former was developed to provide a solution to the latter. Finally, it must be noted that the content of this write-up is more about the basics of statistics and not much of the advanced heresies or applications were considered. The purpose is not to bore the complex context of statistics, but to give the reader a foundation in the field of statistics.